Right, yeah. So, hi everyone. I'm Kayleigh Cooper. I'm the product specialist for MICROMINE Africa, and I'd like to take the opportunity to basically just give you a bit of insight into what a resource geologist does. I'll give you a little bit of an insight into what a resource geologist does on a daily basis. That is my background, and how 3D geological software plays an important role in whatever for a geologist, a resource geologist does. A little bit about myself before we begin, and I hate this part of any presentation, but just to show you sort of the career path that I took to get to my current position and what I actually do now when I started off from varsity. So I studied at the University of Johannesburg, graduated in 2008, and that's where I landed up on the Anglo-American bursary scheme. So I spent all my holidays underground, doing a lot of mapping. And then shortly after that, I landed up stationed at Mogalakwena Platinum Mine as a section production geologist. So I spent every day chasing trucks and chasing drill rigs, but I was more on the production side. A couple of years later, I joined a mining consultancy company as sort of a junior geologist, where they just wanted a geologist. They weren't necessarily looking for that production background, but I landed up being heavily involved in a lot of exploration programs. And this is where I was first introduced to the concept of geological modeling and its influences on resource estimation and mine design. Now, I stayed there for a couple of years and I landed up contributing to quite a few competent persons reports, meaning that I had to build a lot of geological models, and I declared a few mineral resource estimates on specific commodities on different projects on all over Africa. Now, a couple of years later, I decided to join MICROMINE. So this is my current position, where I am a senior technical specialist. And I'm super familiar with the software. So it felt like a natural progression for me. It's something that I've always been keen on doing, is training other geologists. So essentially what I'm doing now is that I'm assisting other geologists who are now in the position I was, being that resource geologist and needing to be familiar with software. So I basically train them on how to use software and how to do estimations within MICROMINE. A little bit about our company. Now, please, you don't have to read the entire thing. You can always go back to the recording. But essentially, MICROMINE is a global company. It was founded in 1986 in Western Australia. And essentially what MICROMINE does is it provides software products that can really be implemented in any part of the mining cycle. Okay, so all the way from exploration, all the way through to extraction, it can really be used in any part. Okay, and that's what we'll kind of touch on in the next coming slides. Now, I'm not the only resource geologist that works for MICROMINE. There are a number of us because we have offices in 18 of the world's mining capitals. Okay, so I'm not the only geologist working for MICROMINE. They need geologists, excuse me, they need mining engineers and surveyors to help get software across to users. A little bit more about what we do, just to give you an idea of where the software is used, but all the different departments that actually need to know geological software. So MICROMINE basically is software. It's named after our company, and it's mainly used on the exploration side of things. So through database management, it's used in the resource modeling workflow, the mine design and planning, but can also be used on the production side. So for example, a geologist's day-to-day activity on site, they need to capture blast hole sampling. You need to capture and store and manage that data somewhere. Okay, so once again, a whole bunch of different geologists needing to use this 3D software. Okay, it's a nice little organogram, but don't worry too much about it. Right, now, what is geological modeling and why is it so important? Well, basically a 3D model represents what a geologist's interpretation of subsurface features are and anything associated to it. Okay, so the structural elements around that. And I'm sure you've heard the adage of you can get 5 geologists in the same room and they'll give you 5 different results. That's exactly what we experience in geological modeling. So it really is up to the geologist to know their data and actually interpret that data as well. The primary input into any geological model is obviously the drill hole data. Now, this is collected from drilling programs with a specific aim to locate and define an economic viable occurrence of any specific mineral. Now, it's not the only data that we're going to look at, but when we look at this data, we need to apply a level of confidence. Okay, this gets applied to the model, and we do this through a mineral resource, and we declare a mineral resource estimate. Now, a mineral resource estimate is basically quantifying the grade in the tons of a specific deposit. So generally, the more you drill, the more you know about your deposit, the more confidence you have in the data. Okay, and this is very important for a resource geologist. You can't just go into the field and grab any sample and say, I'm going to use it. There's an entire validation process that you have to go through. But understanding the geology for the deposit is really, really important, because when you're creating this model, you need to show the structural elements and possibly the depositional complexity. Okay. You also need to reflect any risks associated when classifying a deposit. Okay, and this is all done on the early stages of a project. It's basically your initial drilling. It sets you up right from the beginning. So you've really got to have a lot of confidence in that data. Now, a resource geologist is not going to be that person out in the field. Okay, they're basically going to be handed all this data, and this is what the type of thing they're going to have to look at. And having 3D software just makes that a lot easier for them. Okay. Now, yeah, like I said, the more data you have, the more confident you are in your data. Now, it's not to say that it is the only data, drilling data is going to be used. Now, when we talk about drilling data, it has specific collar points, meaning basically where the drilling has started, survey, so basically the direction of drilling, all your alteration information, all your assay data and lithology. Okay, that's the primary input into a block model, but it's not to say it's the only one that's going to be used. You might have done a preliminary soil sampling program. Okay, this could be done by a geochemist or geologist out in the field. You might have geophysics for the area. This is done by a geophysicist. LiDAR scans, for example, give you a really, really accurate topo surface, and you use the surface to constrain that model. All these data sets need specialists. Okay, so they all need software to actually look and interpret this data. Okay, so when we talk about geological data, we've got this mindset that it's only going to be for the resource geologist, but there's so many other individuals and so many avenues for geologists to go and pick up that software. This is only relating to the actual preliminary model. We keep talking about a geological model, but when you start talking about environmental and social constraints and economic criteria, that's where you account for it in the mineral resource estimate, and that's where a resource geologist will actually step in. Now, the biggest problem faced is how do you take all this information and actually see it collectively? Okay, because you need to interpret, you need to have a meaningful interpretation of your data set. And this is where we use geological software or 3D modeling software. It's a really efficient way to see these different layers on top of one another. And I've tried to show it in the diagram behind. But by having software, you can switch on and off data. You've got the flexibility of creating transparent layers, and you can take nice cross sections through all your data sets, and you can kind of peek into your data. Okay, it's a much more efficient way of working. I would hate to have this all on hard copies, but with that software, you can easily bring in as much information as possible, and you can bring in the information from across different sites as well. Okay, so that transition of data is quite nice. To give you a bit more of insight into what the resource geologist does, okay, because we've kind of spoken about other geologists, is basically I'm going to give you a very, very high level workflow of how to create a resource estimate. Now, I'm not going to go into the technicalities. I don't expect you to know geostats inside and out, but I just want to show you the main points, okay, because this is where geological software kind of shines. Now, there is a methodology to this, but it's not exactly the same for every single type of deposit, okay, but the general workflow is, and the bigger tick items need to be there. Now, the first step in a mineral resource estimate is to actually collect all this data. So like I've mentioned, you've got soil geochemistry, you've got geophysics, you've got drilling data, you've got third-party sources online that has information, and you need to collate all this data and start analyzing it. You need to be confident in the level quality of that data, but this is why you bring it into software. The second step in the mineral resource estimate is now to create a geological model. And when I talk about a geological model, all I'm talking about is a preliminary wireframe model. Now, what on earth is a wireframe? Well, a wireframe is basically a 3D solid. It's like a shell, exactly what you can see on the screen at the top right. Okay, it's a container that's going to be used as the basis for your model. And what we do is we take this entire wireframe and we throw a whole bunch of blocks inside, and we call it a block model. Okay, it's really the container. It's where we're going to map our grade into. during the step, you take all the data that you've collected, you validate it. Like I said, you've got the benefits of software. You can identify issues really easily. Overlapping cells, for example, can immediately be highlighted. Typos, geologists, we tend to, I wouldn't say be lazy, we just log things slightly differently, but technically those codes are not always the same. So you can pick out discrepancies in between your logging. But what you do is you create these series of wireframes to represent of what you understand the geology and the mineralization to be. So like I said, I've got this example in the background. We've got sort of this peach type of orange color. This is sort of I've taken a cross section through. Okay, so I should have actually put a little line there. But essentially this large peach wireframe is your lower grade sort of envelope, so low grade material. This was all mapped using assays. And this yellow is sort of a high grade envelope. Okay, but these wireframes now form the base of your final model going forward. Now, they can be built using implicit modeling or explicit modeling, but irrespective of the modeling technique, you need to be super, super careful that you prevent automatic software routines from making programmed assumptions about the geology. Software is amazing. You can do all sorts of things. It does not have the intellectual experience that you have as a geologist on the deposit. So it can be very black boxy. You can throw in as much information as you want into software, but if you don't know what you're doing, you're going to get rubbish out. Okay, so once again, that adage of rubbish in, rubbish out, it's super, super true when it comes to geological modeling. A wireframe that you produce is not always going to be that final wireframe that you're going to use. Now, by creating these wireframes, we define domains, and essentially all it is a constant distribution of data. So it's just a stationary sort of region. It makes data reliable for estimation purposes. Okay, so we have to start separating the data somehow, and we do this by using wireframes. So in this case, it was a bit of an iterative process. We had to select a cross-section. We had to look at the mineralized intersections of each borehole, and then basically plot all these samples, probably on a histogram or a frequency chart, and assess the statistics to say, okay, is this a domain? And you're kind of going, so what? What if I don't have a domain? Well, like I said, it creates that stable data set to assist in the interpretation of your data. While you do this domaining, it actually gives you an idea of what estimation method to use. Okay, we can't just throw grade at a model. We have to take a bit more of an educated approach, and we start looking at grade interpolation methods. And I'm sure you've heard about, kriging, investors weighting, so ordinary kriging, simple kriging, multiple indicator kriging. There's so many different versions out there. But while you're busy building these domains and getting an idea of the distribution of your data, you're already in the background knowing which approach you're going to take. Okay, so once again, software, super, super important in helping with that. Now comes the stats part, and I have to admit, at varsity, I never really enjoyed stats. I never really enjoyed the geochemistry side of things. It was something that I barely scraped by because it didn't interest me at the time. You throw a whole bunch of information in an Excel spreadsheet and you kind of generate these graphs and you have to interpret them. I didn't see really any value at that time for them. I've done a complete 180 on that. I actually enjoy working with geological data in software and trying to analyze the statistical distribution and the statistical properties of your data sets, because it's amazing the type of information you can actually generate. So there's a whole exploratory data analysis side when it comes to mineral resource estimates. You need to know your data. What's the ranges? What are your high grades? What are your outliers? And you do this as part of your domaining. So this data set with the histogram is based on those two wireframes in the background. Now there is a small wireframe on the inside. Those are those higher grade zones. And by purely plotting the frequency of those samples, we were able to actually generate a lot of information. So for example, we've got this very low grade component. I mean, it's quite a lot of samples, are almost 0%. Okay, so generally those are the samples that are maybe sitting in the footwall and the hanging wall that sometimes you have to analyze, okay, to create those nice hard boundaries. The first population we've identified just by this drop in the peak gives us an indication of a potential geological cutoff. And that's pretty cool. You know exactly now, well, not exactly, but it gives you an idea of what that geological cutoff is. You can check data against that. We can definitely see we've got this low grade, medium grade sort of component. And then we've got a nice peak of high grade. So technically my wireframes are kind of making sense already. I can see there's a lower grade component, a higher grade component. However, each population heavily overlaps by these bell curves. We can see that just at the bottom here. So there's definitely sample mixing. Okay, and this plays an important role when it comes to actually mapping those grades because I've got no clear-cut boundaries. Although I've got my two domains, if I have to evaluate them separately, it orders the data, but at the end of the day, I do have quite a bit of sample mixing. Okay, so I actually do enjoy looking at the stats side of any data. Okay, so like I said, exploratory data analysis, you're getting to grips with your data. The fourth step, okay, sure. Now this is where things start getting a bit technical, but basically depending on the type of method you're using now, or the type of interpolation method you're going to use. So essentially, how are you going to put the grade into any model? It might involve calculating experimental, directional, and omnidirectional variograms. Once again, when I started out in the production side of things, I heard of these amazing resource geologists that spoke about variograms, and they would complain about how they were told to go and generate one by hand, which I completely understand now is so worth doing. So you can know what's happening in the background. But I was very scared to kind of get into that realm because, I mean, look at these graphs. What on earth is it actually trying to do? But if you actually take a step back and you have proper training, say from a resource geologist working at a software company, it's actually not a bad process, especially when you get data like this that is so ordered and stable. It's an absolute pleasure to work with. Okay, so this is part of kriging. It's one of those interpolation methods. They kind of fall into two groups. You get a classical and a geostatistical types of grade interpolation. Now, ordinary kriging is more of a classical side. It's just terms that are used. But as soon as somebody mentions kriging, they have to get an idea of the trend of their data. Okay, so is there an anisotropy present in their data set? Meaning, is there a preferred direction? Okay, it's not always going to be a long strike. It depends on the depositional environment of a specific deposit. But a geologist needs to understand this. A resource geologist needs to understand this. And if you've domained your data correctly, then you're able to see those distinctions. Just to jump onto that, okay, so once you know how you're going to put your grade into your block model and you've got your domains and your wireframes are super awesome, and you can go now and actually map blocks within your wireframe. Okay, the reason we do this is to actually show the variation of your grade. Okay, so we can see the high grades and the low grades, and then you can do a whole bunch of, now I'm going to try and say this without messing it up, but quantitative kriging neighborhood analysis. There we go, got it. QKNA. So all you're doing is you're basically just checking the combination of all your stats to make sure that you've got a really reflective block model. Okay. It also helps to determine how big these blocks should actually be. You don't want them too small, you don't want them too big. It does have an overall play on the stats of your block model. Now, I've heavily simplified the way to create this block model. Trust me, it is not that easy. You sit there for days, if not weeks, but you've got software to help you to do that. If you had to do it by hand, it would take you much longer. But when you're working with this, like I said, the fact that you're working in that 3D environment helps with interpreting your data more accurately and effectively. Because you can validate data on the fly, you can identify issues really quickly, and especially when you've got to update your information. So for example, it's you're extending your drilling campaign, or there's a completely new drilling campaign, you have to bring all that data together and update the model. Okay, doing this in software is super easy. Making sure I haven't skipped any slides, there we go. So I've kind of spoken about what a resource geologist does. We think there are these geologists that sit behind a computer in their nice clothes and their nice suits, and they build these amazing models. And to be honest, that's probably true. But you can have other individuals who, as long as they got the expertise in software, it can benefit them. So like I mentioned before, an exploration geologist needs to plan a drill hole campaign. So they can design that in software. They can pull drilling reports on a daily basis as drilling happens. And they can pull that at face value. When you've got a soil geochemistry program, you need to go and plot your samples, try and identify trends. Maybe you want to build grids. There's production geologists. They need to capture blast hole sampling on a daily basis. And all of this doesn't have to be on Excel. It can be incorporated into 3D software. Okay, so there's a lot of scope for different types of geologists, not just a resource geologist. All of these geologists, even a database manager, their background is geology. They've got that qualification. So it's not just an exploration geologist, production and resource. There's a lot of players in between. You can even have a geological modeler who doesn't necessarily have the accreditation to be a resource geologist. Not that we want to encourage that you go and build models and go and declare stuff without having that accreditation, but you can go build those preliminary wireframes and check the domaining and build the preliminary block model, hand that over to the resource geologist who does the grade interpolation side of things, and they sign off to say that they're competent, or they're confident in your competency as well as their competency. I hope that shed a little bit of light on what, not necessarily what I do, but what I help other geologists, resource estimation, resource geologists do. And just to give you an idea that there's a low scope for different types of geologists, especially in the geological modeling side of things. I don't know if there's any questions, or if Nolene, you want to maybe leave it till right at the end. I'm happy to hang on.
Great, thanks so much.
Yeah.
Good.